Hello, welcome. In this short video, let us look at the derivation of scalar Kalman filter. That is, given a scalar state equation and a scalar observation model, we want to derive the filtering algorithm for estimation of the dynamic state. So the scalar state equation can be defined as, or the given scalar state equation is S of n is equal to a times S of n minus 1 plus U of n. Clearly, the state we are interested in is S of n, and it is related to its previous state S of n minus 1 through this relation, where U of n is it's basically a noise, follows a Gaussian distribution with mean 0 and variance equal to sigma square U, and the initial state S of minus 1 also follows a Gaussian distribution with the initial mean mu s and variance equal to sigma square s. In this derivation, we will assume that the initial mean mu s is equal to 0. This is an assumption. So the scalar observation model is given by x of n is equal to S of n plus W of n, where W of n follows a Gaussian distribution with mean 0 and variance equal to sigma square W. X of n is our observation at the instant n, that is, the values of n can be from 0 to n minus 1. And S of n is the signal component, the time varying signal component, that is what we are interested in estimating, and W of n is of course the noise in the system that follows a Gaussian distribution with mean 0 and variance equal to sigma square W. The goal of Kalman filter is to find, so the goal is to find an estimator of S of n given the observations from x of 0 to x of n. Given these n plus 1 observations, we want to basically find the best estimator for the S of n. So this can be viewed as a filtering problem. By using the Bayesian approach, we can clearly see that the minimum mean square error solution, that is the MMSE solution or MMSE solution, is given by S hat of n given n, which basically symbolizes expectation of the observation S of n given the observations x of 0, x of 1 up to x of n. So this conditional mean, that is conditional mean of S of n given the observations, is the optimal estimate of the unknown parameter S of n, or unknown state of the parameter S of n. In order to derive the Kalman filter, we are going to use several existing formulae, such as this one, where we have lemma 1 is when x1 and x2 are uncorrelated. It is two data points x1 and x2 are uncorrelated, then the expectation of the unknown parameter theta with respect to these two data points x1 and x2 is clearly equal to expectation of theta given x1 plus expectation of theta given x2, provided that the prior mean, that is expectation of theta without any observations, is equal to 0. So provided that this is true, we can clearly split the expectation as a sum of the expectations with respect expectation of theta given x1 and expectation of theta given x2. And the second lemma is, if the unknown parameter theta can be written as theta 1 plus theta 2, that is as a sum, then expectation of theta given a data vector x is equal to expectation of theta 1 given x plus expectation of theta 2 given x. So we are going to use these two lemma for deriving the filter equations. Now let us look at the definition of the conditional mean, that is s hat of n given n, which is equal to conditional expectation of s of n given the observations from x of 0 to x of n minus 1 and the latest observation x of n. And we know that the latest observation x of n is actually dependent on the previous observations from the state model and the observation model. So that is x of n depends on the previous observations from x of 0 to x of n minus 1. So as a result, this lemma cannot be directly applied to this expression, to this conditional mean. So we define a new term x tilde of n, which is equal to the difference between x of n and the expected value of x of n given n minus 1. So basically we are defining a new term which can be seen as an innovation within the observation x of n, which basically removes all the dependencies with respect to the previous observation. So this is an innovation term that is independent of previous observations, that is x of 0 to x of n minus 1. And this term, that is x hat of n given n minus 1, is clearly the term that defines or depicts the dependence on previous observations. So this is the term that depends on the previous observations, and the difference is obviously independent of the previous observations. So the latest observation x of n can be written as x tilde of n plus the term that defines the dependence on the previous observations. So one term basically is independent of the previous observations, and the other term is quantifying the dependence on the previous observation. Now let us denote capital X bar of n minus 1 as a vector of observations from x of 0 to x of n minus 1. Basically x bar of n minus 1 is a vector of previous observations. Now we can rewrite the conditional expectation, that is s hat of n given n, as expectation of s of n given vector x of n minus 1, that is all the previous observations, and the innovation in the most recent observation x tilde of n, because sum of these two components are sum of the function of these previous observations, and the innovation x tilde of n will give us the latest observation x of n. So the original conditional expectation can be written as this new structure. Now, and since x tilde of n is independent of x bar of n minus 1, we can apply the lemma 1. That is, the expectation can be written as sum of the two individual expectations. So we have expectation of s of n given x bar of n minus 1 plus expectation of s of n given the innovation in the most recent observation. So s hat of n given n. Now by looking at the definition of s hat of n given n, we can see that the first term is actually equal to s hat of n given n minus 1. That is estimate of the state given the previous observation before observing the latest observation, and plus conditional expectation of s of n with x tilde of n, s hat of n given n. Now we have to basically determine both the terms. So let us look at the first term, s hat of n given n minus 1. We know that the scalar state model is given by s of n is equal to a times s of n minus 1, that is the previous state, plus a noise component u of n. So by using this definition, we can write that s hat of n given n minus 1 is equal to expectation of s of n given x bar of n minus 1, which is equal to, so by using this model, we have expectation of a times s of n minus 1 plus u of n given x bar of n minus 1. And now by using the lemma 2, that is when theta can be written as a sum of two parameters theta 1 and theta 2, we can basically split the expectation. So this is equal to expectation of a times s of n minus 1 given the observations up to n minus 1 plus expectation of u of n given x bar of n minus 1. This is equal to a times expectation of s of n minus 1 given the observations up to n minus 1. And this term is obviously 0 because expectation of u of n given x bar of n minus 1 is equal to expectation of u of n. Since u of n is clearly independent of the previous observations, this expectation should be equal to 0. Therefore, s hat of n given n minus 1 is equal to a times s hat of n minus 1 given n minus 1. Since this is clearly the definition of s hat, the definition s hat of n minus 1 given n minus 1. So, thus we have the first component of the conditional expectation. Now we need to find the second component, which is expectation of s of n given x tilde of n. In order to find this conditional expectation, we have to use the following lemma. This is lemma number 3. So given a vector z which has two components x and y, both are following a Gaussian distribution and have a correlation, that is x and y are correlated Gaussian random variables, then conditional expectation of x given y is equal to expectation of x plus covariance of x and y divided by variance of y multiplied by y minus expectation of y. Now by denoting x as s of n and y as x tilde of n, we can write that expectation of s of n given x tilde of n is equal to expectation of s of n plus covariance of s of n and x tilde of n divided by variance of x tilde of n multiplied by x tilde of n minus expectation of x tilde of n. This is basically the prior mean, which is assumed to be 0, so we can ignore this term, and since the mean is 0, and since x tilde of n is equal to x of n minus x hat of n given n minus 1, which is basically the estimate of x of n given the n minus 1 observations, so the expectation of x tilde of n is clearly equal to 0. Therefore, covariance of s of n comma x tilde of n is equal to the correlation between s of n and x tilde of n, which is expectation of s of n multiplied by x tilde of n. And the variance is, of course, expectation of x tilde square of n. Therefore, expectation of s of n given x tilde of n is equal to the Kalman gain kn multiplied by the innovation term x tilde of n, where k of n, the Kalman gain, is equal to expectation of s of n multiplied by x tilde. There is correlation between the signal component s of n and the innovation term x tilde of n and the variance in the innovation term. Now our goal is to derive an expression for the Kalman gain, which is K of n is equal to expectation of S of n multiplied by the innovation term, which is defined as x of n minus x hat of n given n minus 1, divided by expectation of x of n minus x hat of n minus 1 whole square. Now we need to understand what is x hat of n given n minus 1, which is clearly equal to expectation of x of n given the observations from x of 0 to x of n minus 1. And since from the observation model x of n is equal to s of n plus w of n, we have expectation of s of n plus w of n to x of n minus 1, which is x bar of n minus 1. And now by using the lemma 2, that is when the parameter can be written as the sum of two parameters, theta 1 and theta 2, we can basically split the expectation. So this is equal to expectation of s of n given x bar of n minus 1 plus expectation of w of n given x bar of n. The second term is clearly equal to 0 since expectation of the noise is assumed to be 0. So we have x hat of n given n minus 1 is equal to s hat of n given n minus 1. Therefore, the Kalman gain k of n becomes s of n multiplied by x of n minus s hat of n given n minus 1. Basically we replace x hat of n given n minus 1 with s hat of n given n minus 1. So by inserting s hat of n given n minus 1 in the place of x hat of n given n minus 1, we have expectation of s of n multiplied by x of n minus s hat of n given n minus 1 divided by expectation of x of n minus s hat of n given n minus 1 whole square. Now we have to manipulate the numerator. So we have to use the following relation. That is x tilde of n is equal to the difference between x of n and x hat of n given n minus 1. And then expectation of x tilde of n multiplied by s hat of n given n minus 1 is equal to 0 because x tilde of n is independent of all the previous observations and s hat of n given n minus 1 is dependent on the previous observations, so their correlation is obviously equal to 0. So we can basically add this term to the numerator. So the numerator becomes expectation of s of n multiplied by x of n minus s hat of n given n minus 1. And since this term is equal to 0, we can basically subtract this term from the numerator. So we have minus expectation of s hat of n given n minus 1 multiplied by x tilde of n, which is equal to x of n minus s hat of n given n minus 1. So now by taking this difference term common in the both expectations, we have s of n minus s hat of n given n minus 1 and x of n minus s hat of n given n minus 1. Clearly this is equal to expectation of s of n minus s hat of n given n minus 1 multiplied by s of n plus w of n. By using the observation model, we have s hat of n given n minus 1. So this is equal to expectation of s of n minus s hat of n given n minus 1 whole square, and the expectation of the product s of n minus s hat of n given n minus 1 with the noise component w of n is clearly equal to 0. So we can ignore that term. So this is the numerator. We can do similar manipulations on the denominator and we will find that it is equal to expectation of x of n minus s hat of n given n minus 1 whole square is equal to sigma square w plus expectation of s of n minus s hat of n given n minus 1 whole square. Now let us denote this expectation of the difference square as m of n given n minus 1, which is basically the minimum prediction error, is equal to expectation of s of n minus s hat of n given n minus 1. So this is the true value and this is the predicted value. So the square of the expectation of the square difference is clearly equal to the minimum prediction error. So the Kalman gain is equal to, the numerator is equal to m of n given n minus 1 and the denominator is equal to sigma square w plus the prediction error. Now let us look at the recursive relation for the prediction error, which is m of n given n minus 1 is equal to, by definition as we denoted it, expectation of s of n minus s hat of n given n minus 1 whole square, and this is equal to expectation of, by using the scalar state model, we have a times s of n minus 1 plus u of n minus s hat of n given n minus 1 whole square, and since s hat of n given n minus 1 is equal to a times s hat of n minus 1 given n minus 1, this can be easily derived from the scalar state model. So by using this relation, we have m of n given n minus 1 is equal to expectation of a square multiplied by s of n minus 1 minus s hat of n minus 1 given n minus 1 whole square plus expectation of u square of n. We basically ignored all the cross terms. So the recursive relation for the prediction error is given by m of n given n minus 1 is equal to a square multiplied by m of n minus 1 given n minus plus sigma square u. So this is the recursive relation for the prediction error. Now let us look at the expression for the s of n given s hat of n given n, that is the update of the state given all the observations up to n, which is clearly equal to the two terms. The first one is given by s hat of n given n minus 1, that is s hat of n given n minus 1, that is the prediction plus the Kalman gain multiplied by the innovation term, which is x of n minus the prediction. So this is basically the corrected update of the estimate. Now finally let us derive the recursive expression for the updated error or the posterior error, which is m of n given n, which is by definition equal to expectation of s of n minus s hat of n given n whole square. So this is basically the error in the update, which is equal to, by using this expression, we have expectation of s of n minus s hat of n given n minus 1 minus the Kalman gain multiplied by x of n, the latest observation, minus the prediction s hat of n given n minus 1 whole square. So now by treating this as by treating this difference s of n minus s hat of n given n minus 1 as the first term a and this term as b, we have expectation of a square plus b square minus 2ab, which is expectation of s of n minus s hat of n given n minus 1 whole square plus k square of n, that is the b square term, expectation of x of n minus s hat of n given n minus 1 whole square, and the 2ab term is equal to minus 2k of n, that is minus 2 times the Kalman gain multiplied by the AB term, S of n minus S hat of n given n minus 1. That is basically the error in the update and the error between the prediction and the true value, and then x of n minus S hat of n given n minus 1. And this is equal to, and this is by definition m of the mean square error of n given n minus 1. That is basically the prediction error, plus k square of n, and this is, and the expectation of x of n minus S hat of n given n minus 1, that is the difference between the observation and the prediction, that is the mean square error of the observation and the prediction, is obviously equal to the noise variance plus the prediction error. This can be easily verified by looking at the definition of Kalman gain. Basically, this denominator is the value given here, and the last term is clearly equal to 2 times the Kalman gain multiplied by the expectation of this product, which is equal to the prediction error. Because the expectation of the product between this difference and the noise component W of n is clearly equal to 0. And note that x of n is equal to S of n plus W of n. Therefore, the first two terms basically form the prediction error, and the product of W of n with this difference is the expectation of the product of W of n with this difference is clearly equal to 0. So we are left with these three terms. Now by using the definition of the Kalman gain, we have k of n, that is basically sending this denominator onto the left side, we have k of n multiplied by the sum sigma square W, that is the noise variance, plus the prediction error is equal to the prediction error itself. So we replace the product k of n multiplied by this sum as m of n given n minus 1, that is the prediction error. And finally here we have 2 times k of n, the prediction error. Therefore, the update error m of n given n is equal to, by taking the prediction error common in all these three terms, we have 1 minus the Kalman gain multiplied by the prediction error. Thus, we have all the expressions or the equations required for the scalar Kalman filter. So, we have the prediction. This is the prediction equation, that is S hat of n given n minus 1 is clearly equal to a times the previous prediction. S hat of n given n minus 1 is equal to a times the previous estimate, so, or the previous update. So this is equal to S hat of n given n minus 1, that is the prediction for the new observation. The prediction term before using the new observation is equal to S hat of n given n minus 1 is a times S hat of n minus 1 given n minus 1, that is the previous update. Then the prediction error is given by m of n given n minus 1 is equal to this equation. There is a variance in the error term in the scalar state model and the a square multiplied by the previous update error. So which is equal to sigma u square plus a square multiplied by the previous update error. And then we have the Kalman gain, which is equal to k of n is equal to the prediction error m of n given n minus 1 divided by sigma square W plus m of n given n minus 1. This is derived right here. And next we have the correction term, which is given by this sum, that is the update is equal to the prediction plus Kalman gain multiplied by the innovation term. So which is equal to S hat of n given n is equal to S hat of n given n minus 1, that is a prediction, plus the Kalman gain multiplied by the observation minus the prediction. And finally we have the update error. Update error, that is m of n given n, which is equal to 1 minus Kalman gain multiplied by the prediction error, which is 1 minus k of n multiplied by the prediction error m of n given n minus 1. These 5 equations basically constitute the scalar Kalman filter. Thanks for watching.